This is our coherent optical setup here at OFC. I'm Rob Marsland. I'm going to tell you a little bit about what we're showing here. So what we have on this side is a transmitter that is creating a 64 QAM 32 gigabaud signal that can be used for testing coherent systems. This signal has an aggregate data rate of 400 gigabit per second. The way we're doing this is we're using two of our arbitrary waveform generators. These run at 50 gigasamples per second, and we can load a waveform to create the in phase and the quadrature portions of the 64 QAM waveforms. These two are synchronized together by the box in the middle. These two waveforms then go to our OM5110 optical transmitter box, which basically upconverts the IQ baseband signals to the optical frequency. So coming out of here then we have the 64 QAM optical signal. But we're going to get more than one of those because we are putting two lasers into the modulator. So this is a modified OM2012. It has two lasers inside, but we've modified it to combine the two lasers into one output. So we're getting two separate laser frequencies in this fiber that are both being modulated at the same time. So we're getting two carriers then of the 64 QAM 32 gigabaud signal. So then that's amplified by this little optical amplifier here, and then it goes across the table over to the optical modulation analyzer. So over here what we have is the two of our 70 gigahertz single channel oscilloscopes. These are the new SX models. So they have a 70 gigahertz input at 200 gigasamples per second, but also they have two of the 100 gigasample per second inputs as well. Here we're using the 70 gigahertz input that is coming from our receiver. So this is the OM4245 optical modulation analyzer that receives the coherent optical signal. It goes in here and is down converted by the local oscillator to produce the baseband once again, so that we can then recover the data that we transmitted in the first place. But these signals now need a lot of analysis because after optical down conversion, there's still a lot of work to do and to recover the optical phase and the clock frequency and the polarization and finally get the bits out. So we're going to digitize these analog waveforms with the oscilloscopes, and then we have an application running on the oscilloscope that will serve the data up to our coherent analysis software. That software package can run on the scope, but right now we're running it over on the PC. The data is transported over Ethernet to the PC where it's processed. So up here on this monitor then we can see the results of analyzing the output of the transmitter. The transmitter, it produces approximately 6% EVM for the 16 QAM and 64 QAM optical signals. With that EVM level, you wouldn't be getting such a nice constellation. What's new here is our newest version of our analysis software has some very powerful receive side equalization filters. These filters can be used to show just what is the origin of any sort of impairment to the signal by removing all frequency domain impairments so that all that's left would be impairments due to noise or nonlinearities. So we have that adaptive filter turned on, and that's giving us this nice 64 QAM constellation with an EVM 4%. The other thing we're showing here, in addition to the strong receive side equalization, is the multi-carrier capability. So we're not just receiving one 64 QAM signal, we're receiving two 64 QAM signals. You can see the two carrier frequencies here and here. So right now we're focusing on this particular carrier. We're selecting it with a digital filter, and then that's the one that's being analyzed, and this other one's being thrown away. But we have the ability to switch back and forth to analyze both carriers. So then you have a constellation for carrier 1, a constellation for carrier 2, eyes for carrier 1, eyes for carrier 2. We also have all the measurements for the two carriers. So you can keep an eye on a multi-carrier, in this case 2-carrier optical signal, as well as doing analysis on single carrier signals. So this is our setup to show tools that can be used for developing and measuring the next generation of very high bandwidth coherent optical systems. Thanks.